को मैं एक भेजी हूँ।
Dear all, good morning. I hope I am audible to you. Is it fine? At least one yes, or raise your hand. They're also joining. Okay, last class we discussed about, I will share this screen. Okay. Last class we discussed about some points on the atmosphere. Let us see that how much we know the atmosphere to a great extent. I'll repeat some slides since it is a PPT. It's a good tool for you and for me. The top panel shows here is the life cycle of the sun. Left extreme is the birth, right extreme is the extent of the star, not in terms of visibility, but in terms of its death. Lifespan of a star. Right now we are about 4.5 billion years. A star can live for about 14 billion years, but size is not in terms of scale. Gradually after it becomes warming, may gets converted into a red giant in 10 billion years, then a planetary nebula, then white dwarfs. Okay? Certainly, the staff from astrophysics will touch upon these things. That's it. As far as the bottom panel is considered, you can see here in such a way, left extreme is sun, right side of the planets. Certainly, they are according to the size. Starting from Mercury, may not be able to see still nearest star, nearest planet. Venus, Earth is the third planet, Mars is the fourth. Jupiter, onwards they will call it as Jovian planets. In terms of the size, Jupiter is the largest planet in the planetary system of the Sun. Saturn with beautiful rings, Uranus and Neptune are the two extreme planets. 2016 6 onwards, the Pluto is excluded from the family of a planet. It is called as dwarf planet, along with a race after the Pluto and a series dwarf planets in between Mars and Jupiter. This is a case. Wow, one asteroid. Let us see the picture. Earth's first atmosphere was started in 4.5 billion years ago, post the age of the sun, with no atmospheric constituents and no oxygen in the atmosphere. This is the case. The primary atmosphere was probably composed of the lightest elements, hydrogen and helium. These gases were lost to the space early in the Earth's history because the gravitational force which is influencing the atmosphere to hold them was too weak. And moreover, these are the lightest elements in the periodic table. So, for what we found, weak gravity allowed lighter gases to escape from the gravitational influence of the Earth. Of course, it might have happened, or Similarly, for the other planets too, we get there. The Earth's atmosphere did not always look like this. This is the photography. Here we can see green color shows the forest, greeneries, and this color shows the terrain, of course green also. Blue color shows the ocean. Earth is, our globe is made up of almost 70% of the water bodies, but preferably ocean. White patches here are the clouds, having a sort of disturbances. On the top, you can see both combined effect of clouds as well as the ice, that is the polar regions. The right extreme is the moon, one of the natural satellites, one of the only natural satellite for the Earth. As Earth's atmosphere is considered, almost 99% of atmospheric gases, including the water vapor, extends only 30 kilometers above the surface of the Earth. You see that this is the surface of the Earth actually. Above that, you may be seeing some fantastic and spectacular phenomena of the light, a background light of that kind. It is a real picture. It is not a generated way of that kind. See that. This is a layer. This is a layer about some 30 kilometers to a great extent, where 90%, 99% of the atmosphere is water. About 30 kilometers, hardly we are having 1%. This is the thin gaseous envelope. Still, if you go, still will be there. Means almost our weather phenomena occurs within the first 10 to 15 kilometer range. Why they are putting range? Because maybe about 15 kilometer over the equatorial zone or Bangalore of that kind, we are near to the equator, both magnetic as well as the geographic equator. Here, this equator, what we are referring in atmosphere is geographical equator, not the magnetic equator to a great extent. Of course, while studying some phenomena which are relevant to the geomagnetism, atmospheric electricity, or even eclipse, preferably we will go to the geomagnetic equator. Both are passing through India. In fact, not hills actually, tip of peninsular India, Kanyakumari, or Tumba, that is what we can call Tiruvananthapuram. That line is having a geomagnetic equator or zero equator. In terms of geographical, it is about 5 degrees north to a greater extent. About being this, most of our weather occurs within the first 10 to 15 kilometers. See that. Then second atmosphere has started about 4 billion years ago. Don't get confusion. We are going in a time span of the negative billion means 10 to the power of 90 years. UK, this is in British English. American English, they will use billion for 1 million to a million, that is almost 10 to the power of 12, but follow it an uniform convention of British English. It is about 10 to 1,000 million years or 100 crore years, they can call 1,000 million years. 1,000 years is equal to 1 billion year. When about 1,000 billion years, 4 billion years ago, there was no atmosphere to greater constant with the life to exist on the earth. Outgassing they can call from the volcanic eruptions, which might have included in the atmosphere of the earth. For example, the compositions like carbon dioxide, nitrogen, sulfur dioxide, such type of things were there. This is the second atmosphere we can call. Then so many comet as impacted. In fact, people are saying that comet also possesses a content of water vapor content, actually, water vapor content to a great extent. One of the school of the thought is that water vapor might have brought from extraterrestrial. Inside the earth, there was no water. Water vapor was brought from the outside. Water vapor was brought from the outside. Second atmosphere composition, mostly of the water vapor is 80%. CO2, 200 to 1,000 times more than the present, means almost 10 times. Right now, we are about 400 particles per million. In terms of the number we are counting, particles per million. Means now 10 times it was heavier in the sense larger in concentration. As the concentration of carbon and carbon dioxide or compounds of carbon, for example, carbon monoxide, carbon sesquioxide, CO2, C2, CO3, C2O5, of that kind, if such type of things increases in any of the planet, invariably the temperature has to go up. because the compounds of carbon are the one where they can absorb energy, and after absorption, they radiate energy back to its environment. Radiate energy back to the environment. That's why if we compare the composition of Mars, compare the composition of Earth, compare the composition of Venus as having a highest carbon dioxide, and the temperature is far, far ahead, almost more than 200 degrees Celsius compared to that of the Earth. Means to say, our intention is that earlier atmosphere of Earth was enriched with the carbon, and the temperature was also quite high. Small amounts of nitrogen were there, small amounts of sulfur were there, methane was there, and even trace amount of oxygen. Very tall, of course, and a dense atmosphere, almost no oxygen. Tall in the sense it is not thick, thin atmosphere they can call, but a dense atmosphere. Need not be restricted for 30 kilometers. What I told in previous slide, there is still more than that. Days. Then two major events came into the play, particularly the lightning activity. Those lightning activity has cooled down the atmosphere from several degrees, several tens of degrees of temperature to the global average temperature. Thereby, it brought Earth, and Earth could precipitation started. Precipitation started in the sense rain started. Formation of cloud has happened. Rain resulted in the fundamental changes to the atmosphere. Remember, here precipitation is falling off the rain, is that water droplet, smoke, fog, mist, snow, all put together they can call. The atmosphere got cooled with water vapor content. Those water vapor condensed to form a water droplet and has fallen onto the earth. Solid earth was also a relatively a hotter surface that also got cooled gradually, and the water occupied almost 70%, making the life possible on Earth. Most of the water vapor moved from the atmosphere to the global oceans. Most was removed also in dissolved into rainwater, some of them into the ocean surface. Carbon acid leached into the rocks and deposited with the carbon. This is for your understanding, don't worry. Atmosphere became much thinner rather than thick. Most of the atmosphere was locked up on the Earth's surface, near the surface. Then life emerged towards the modern atmosphere almost 2.8 billion years ago. This was the first sign of the existence of the life on Earth with the cyanobacteria. First prokaryotic cells have formed about 2.8 billion years ago. This is a 4 billion year. This is the present actually, if you go back actually. Then origin of plants has occurred about 0.5 billion years ago. Origin of flowering plants has happened almost about 5 billion years ago. Make the convention of the billions. It does not depend on the lifespan of a human being of hardly 100 years at most. Cyanobacteria formed and photosynthesis started. Carbon dioxide plus water vapor in presence of the light gave the energy due to the photosynthesis and the liberation of oxygen into the atmosphere. This cumulatively was increasing and reached the level of about 20.9% right now what we are having. That will see later. Sorry, we'll see later. Oxygen became an abundant in the Earth's atmosphere and is a sign of life. Good. Thanks to the nature, thanks to the planetary system, thanks to the Earth, where we are hearing, you are hearing me, and I am able to address these concepts because of maintenance of temperature or maintenance of the temperature on the Earth to a great extent. See, I don't know, depending on your size of the display, you can notice it. This is the sunrise, which is about 5.5 degrees south, means that is 5 degrees below the equator. See that this is the solid earth, black color. Above that is the Earth's atmosphere. As a photograph taken from the satellite, was taken in the early morning, and the sun was still below the horizon. See that, still below the horizon, and not yet illuminating the dark band of the low-level clouds on the Earth's limb, ranging almost about 13 to 18 kilometers above. These low clouds It's a brown layer of the tropopause. Tropopause they can call actually brown color. Okay. And atmospheric temperature inversion, which isolates the troposphere and from the stratosphere. This is a stratosphere at almost 50 kilometer. 50 kilometer. This is about 13 to 18 kilometer range of that kind. Inversion is nothing but rather than temperature starts decreasing, it may increase in the stratosphere. That is why inversion you can call. You can also call inversion temperature starts increasing in stratosphere, then later it decreases in the mesosphere. That and another inversion you can expect. That will try to see the structure of the atmosphere temperature in terms of the different layers later. Inversion means instead of following some trend, the trend gets reversed. The trend gets inverted actually, which isolates the troposphere from the stratosphere together and effectively concentrates the particles and the atmosphere both above and below this level. That is why how this picture is happening. Got you. This is the polar region, a sea ice, a snow, whitish in color. This is the continental ice sheets. Okay, this is a landmass. Landmass. Blue color is perfect. Blue color is the ocean environment. To take a photography from the space near to the planet Earth, how it looks actually. I will go through some of the pictures to make you to convince the atmosphere and its role. What you are observing here is that a photography taken from above water body, maybe may not be a ocean, maybe a huge lakes, maybe a river, reservoir of it, and also can happen naturally. See, these are the white patches of the cloud, an air with water body to stray clouds. Here, this makes a shadow also here, a solid head. Small patches. See the dimension of the clouds, it may extend for several hundred kilometers. They are not small in dimension. Go through another flight, see the moon in the background. See the fantastic phenomena which is happening continuously on the earth to balance the temperature. Always, these clouds and atmosphere makes the earth a comfortable zone for the human being or to life exists on earth, making the temperature of the equator relatively cooler and relatively warmer, and the polar regions are relatively cooler. See that. In the background, you can see the satellite. This is the atmosphere profile. I can see the troposphere, maybe stratosphere, mesosphere. Here you can see right extreme, some greenish in color of that kind. Maybe we'll see that Aurora Borealis and Aurora Australis, which are happening at a height of about more than 100 kilometers, that can witness in the atmosphere. Wow, a cloud with shadow, you can see that. This is only for your curiosity I'm thinking, since thanks to the multimedia technology of the multimedia, where I can demonstrate these pictures. I can't draw that on the two-dimensional board actually. Okay? Oh, this is a group of the clouds which are scattered here and there. Photography was taken from the top actually. Since horizontal motion, so you can see that above the tropopause, almost more than 15 kilometers. This is the thing. The cloud height can start from 1.5 kilometer to 1 to 1.5 kilometer. That is a cloud base they can call. It may go to the extent of 15, 16 kilometer, sometimes 18 also over the equator. If you want to go above the clouds, you have to fly above a 17, 18 kilometer. Then only you can have this type of picture. All aircrafts, particularly national and international aircrafts, will fly at a height of more than 10 kilometer. 10 kilometer. This is another picture with moon and background. Wow, this is what I want to convince you actually. See that this earlier also you have noticed. See, something is moving from the bottom. Okay, air mass rises up, clouds moves up, clouds something moves up against gravity. No issue because of the buoyancy. They are flying because the gravitational force attracting them towards the earth has to match with the buoyancy force. Buoyancy force is a force which is caused by the rising of the air mass, rising of the air molecules upward, vertically upward. Like for example, if you blow a balloon with a hot air or maybe relatively a less dense air, depending on density, the balloon will fly up. And as it goes up, the balloon dimension expands because the density of the air inside the balloon is lesser, it expands and try to acquire the intense pressure equal to that of the surface, equal to the environment. If once it exceeds, certainly the balloon will burst. That is different scenario. But you see here actually, here something is happening. Something is happening, almost like stopped. It is moving. It is. This is at a height of about 15 kilometer. I am telling you, you accept it. There is no way. Okay. At a height of 15 kilometers, something is stopping actually. For example, if you while cooking, maybe for example, if you are increasing the, if you want to raise the temperature of the milk, if you close the lid of a vessel or container, maybe what milk will temperature of the milk will rise up and then it starts increasing, and milk will never evaporate outside the container because the lid will be there. Here, similar to that, there is some lid. Something is forcing not to escape, not to escape. What is this lid? Where is it there? At what height you are getting? What are the causes? That we will see that. They are calling this as the anvil, A-N-V-I-L, anvil. Wind is moving from right to the left. That's why it is showing this like that. Almost like a what you can call umbrella, like an umbrella of that kind, some dimension of that kind actually. Okay, this is or maybe like a mushroom to a greater extent, some different dimensions you can call actually. This is something is okay. The dimensions of the order of more than 100 kilometers to a greater extent, particularly this diameter actually. That we'll see in physics, how that physics plays an important role, how the physics concepts plays an important role that can stop something in the air for a quite longer duration. This is a beautiful picture with the scattering phenomena. Means because of the different particles in the environment, different sized particles in the environment, different nature of the particles in the environment, we are getting different colors, either maybe reddish or maybe bluish or gray color or mixed color of that kind. If there is no atmosphere, if there are no particles in the atmosphere, for example, if it is only a solid earth, solid planet, you can't expect any this type of a phenomena, maybe apart from the weather phenomena of that kind. Yeah, groups of cells of the clouds, it's also making it is test. Wow, it looks like a very bright thing actually. See, this looks like a clouds, white clouds, green clouds, yellow clouds, and golden clouds, silver clouds. People are calling with different names. Poets have called with a different nomenclature. That is mainly because that has intuited, excited them to write so many poetries, so many novels on clouds. Meghaduta is one of the example, classical example. But at the same time, all clouds which appears very beautiful like silver clouds are so dangerous. Dangerous in the sense we are unable to enter into the clouds, or are unable to come out of the clouds because they are highly convective clouds. They are highly dynamic clouds. They are dangerous because the dynamics is happening within the clouds is not on a regular fashion. The air mass may move very fast, about almost 10-15 kilometers. It can travel within a half an hour and it can come back. That is why during thunderclouds, during thunderstorms, during storm time, where lightnings are happening, where huge clouds are moving with a relatively higher speed, you might be noticing some kind of a clouds of that kind. They are called cumulonimbus clouds. They are the one which can cause tremendous damage by delivering the energy, by transferring the energy, by transporting the energy, both vertical as well as horizontal. Maybe to a greater extent, vertically it should be quite large. These are different three cells. Okay, another one. My God, a person is standing. You can see that continental ice. Continental ice is nothing but you can walk on the continental ice. Scientists are trying to extract what the Earth's atmosphere was composed of a long time, about 10 years back, 100 years back, 1,000 years back, 1 million years back, 1 billion years ago. How can we know that what was the composition at that time? What happens, you might have heard actually, few trees, rings will happen every year. Means there is a formation of a ring and completion of one cycle of the earth around the sun. There is a match. There is a coherence. There is an what you can call correlation. Means if assume that a tree is about some 20 rings, we can say that the lifespan of, not lifespan, the life of this tree was about some 20 years. It was formed. Means that is the bark of a tree. When you take that is the count, they will count the range. Here what happens in ice core, either polar regions or maybe at a greater point, wherever that continental ice forms, actually, atmosphere is there. Continuously, the ice means the water gets condensed in the form of an ice. While condensation, the air molecules will be locked. Air molecules will be locked and will form the solid ice. That solid ice layer will grow. Our thickness of the ice will grow with the time, with the evolution of the time. Means the molecules which were trapped in the ice will go down and deeper, and it will be locked forever. For example, if you dig for about 1 meter, 10 meter, 100 meters, then you can say that what must be the composition of the atmosphere where atmosphere long back. The scientists also paleoclimatology they can call. The scientists also estimate in such a way that what rate the thickness of the ice layers will grow up. For example, about 1 millimeter for about 10 years, or 1 millimeter for 1 year, or 10 millimeter for about 100 years. Then if they dig about 100 meters, then they can say that what must be the possible composition of that. This is the sea ice. They can call entire sea under cold temperature become converted into the ice. This is a one beautiful picture. Looks like a picture for you actually. Because ice sheet means where the ice sheet meets the sea. See that actually means New York looked like this almost 18,000 years ago. This was a lake. This was a lake actually. During winter, lake gets converted to the ice sheet. People used to walk on the ice sheet to travel from one part to the another part of the one corner to the another corner. Means during summer, the same ice sheet gets melts and it becomes a lake. Yeah, what a beauty actually. The nature is a strong energy to convert from huge blocks of ice into the water and a water into an ice. This is the criteria. This is the strength actually. This is strength. But this is another picture demonstrating you that the right extreme is looking like a bright is the ice core. The left extreme, don't take it as a dark, it is a water body. Ice melts, converts into the water. Water gets condenses, converted into the ice. Both phenomena are happening to every extreme. Ice reflects most of the energy, 100% almost. That's what it looks like. White. Water absorbs energy. It does not allow the light to escape. This maybe few part maybe gets reflected. That's why we are seeing the water body and looks dark. And water absorbs the energy and becomes warmer. And ice does not absorb the energy and becomes cooler to a certain extent. When the structure of the Earth, few slides only, structure of the Earth's atmosphere when it was formed several billion years ago. See that hot core of the Earth, then maybe the same thing. Then this is the outer layer of the solid Earth. Solid Earth. Earth's atmosphere look like that. This is a repetition. 99% of the atmospheric gases, including water vapor, only about 30 kilometers. Where we are getting the energy? Almost we are getting the energy from the sun. Sun is at a distance of about 150 billion kilometers. Still, the atmosphere on the Earth is driven by the solar radiation emitted by the sun. Means we are under the great control of the sun. Thanks to the nature, means we are warming up in the morning. We are warming up in the afternoon. We are warming up till evening. If temperature goes beyond some extent, will come down to a certain extent. Chetan R, do you have any query? Chetan R, no issue. I hope you are able to see that. This is the age. They can call it as an ice-free age to an ice-covered age. When 10,000 years ago, the Earth was completely covered with the ice. Cold planet. Then this phase, second phase, third phase. Right now we are in this phase. If this polar ice caps gets converted to the water body with the continuous enhancement of the temperature, maybe by global warming, maybe by human invention, then the Earth looks like this. There is a transition or oscillation from this phase to this phase. Each phase is about some 10,000 years, what the scientists will say. Yeah. This one concept. Now, let us see that last time I stopped at some concept. Now, we have to discuss on the mass of the atmosphere. You might have taken what must be the weight of a potato? What must be 10 kilogram of an potato, 10 kilogram of an apple, 10 kilogram of an orange, 10 kilogram of an sapota. Similar to that. What must be the total mass of the atmosphere? If you compare the atmospheric thickness, hardly about 100 kilometers. If you compare that, it is almost the dimension of an Earth is with the orange, okay? The skin of an orange almost looks like the almost thickness of the atmosphere. Since with simple principle, I'm sharing this one also for you. At any point on the Earth's surface, the atmosphere exerts a downward force on underlying surface due to the Earth's gravitational attraction. Means all molecules are gets attracted, all atmosphere gets attracted, all constituents are gets attracted downward. The downward force, that is the weight, what we are calling of an unit volume of an air with the density is given by rho is the density, mass per unit volume gives you the density must be equal to the force acting on the air mass should be directly proportional to the density times the acceleration due to gravity. Fine. The atmospheric pressure on the Earth's surface is due to, PS is, here the suffix is missing, is due to the weight per unit area. That is the same thing. W you can call weight per unit area, surface area of the A in overlaying column. Starting from 1 meter square or 1 foot square till to the extent of the top of the atmosphere. If you take the entire air mass, how much it should be there? That is the pressure which is acting. Pressure is nothing but force per unit area. Force per unit area. Either you push a table from your hand palm or you pull, that is push or pull. Or if you put your hand on the table and pressurize, that is the force you are applying on the table. This is a force per unit area acting due to the entire weight of the atmospheric constituents over that column. For example, take a PVC pipe of that kind, about 10 centimeter diameter, and extend it to the top of the atmosphere. The whatever may be the air molecules which are existing, that has to have the force at the surface. That is given by integral from zero surface to the infinity top of the atmosphere, rho times the acceleration due to gravity multiplied with the surface area. In fact, G, acceleration due to gravity, sorry, not uppercase, it is a lowercase. G is the 9.807. Let us assume that both latitude and longitude wise, if you move, it does not change much, only for practical applications. Let us take this as a constant value. If you take this G as the outside, you can call it as a G naught out of the integral. Means the pressure which is acting should be the mass times G naught, where the integral of rho times dz should be the mass, where m is the vertically integrated mass per unit area over the length of the overlaying area. How much it should be there? What must be the total mass of the atmosphere? Let us have an exercise. Of course, you can calculate. I will show you. See what we got it actually in the earlier slide. The pressure, total pressure which is acting should be the mass times the acceleration due to gravity. If not, we are interested in estimating the global average surface pressure 985 hectopascal over the sea surface, or even 10,000 hectopascal also you can take this in. Estimate the mass of the atmosphere. We know this relation, okay? Means these bars indicates the average mass must be equal to average pressure which is acting over that area over the acceleration due to gravity. 985 hectopascal, 985 into hecto means 10 to the power of 2, pascal over hectopascal over 9.807 meter per second square is the acceleration due to gravity. Almost 9.8 gets cancelled here. Okay, small value still. That is why you are getting about 1.004 into 10 to the power of 4 kg per meter square is the average mass. Average mass of the atmosphere over area of a meter square. In 1 meter by 1 meter, you extend it till to the top of the atmosphere, you are getting about 10 tons, 10,000 kilogram. 10,000 kilogram. On your head, always you are having about 2,000 kilogram of air mass, but still we are not feeling because it is spreading out. Then what must be the total mass of the atmosphere? Mass should be the same area extended to the pi r square. Pi m is 4 pi r square, radius of the earth, okay, r square, and the average mass. 4 pi, 6,370 kilometer is the radius of the Earth, you convert it into the kilometer to meters, meter square, and this is the average what you got it from your earlier relation. If you will get mass of the atmosphere for entire on the surface is about 5 into 10 to the power of 18 kilograms. Kg remains constant. This meter square gets cancelled. 5.1 into 10 to the power of 18 kilograms. Remember, work out this numerical problem either for the examinations for your curiosity. Yeah. Water vapor. Okay, now let us see that what the atmosphere is made up of. Atmosphere is made up of different gases. Water vapor is the only one which can transform in all the three phases, either liquid water or gaseous water or maybe the solid water. Air is a mixture. Air is a mixture of nitrogen, oxygen, argon. We'll call them as the dry atmosphere, including carbon dioxide. Okay, but air is also a mixture of dry atmosphere plus water vapor. We'll call them as the moist air or humid air. If you compare the density of the dry air and moist air, density of the dry air is relatively more compared to that of the moist air. Because since density of the moist air is less, moist air makes the clouds and clouds are floating, clouds are flying mainly because density of the clouds are relatively less compared to the density of the dry air. That is why they are at some height. Depending on the density, maybe about 1.5 kilometer or 2 kilometer, 4 kilometer, 10 kilometer, 10 kilometer. Why they are floating? Because they are floating by balancing the gravitational force and the buoyancy force. Why they are moving? They are moving under the influence of the pressure from high pressure region to the low pressure region. Always due to the wind, wind moves from high pressure to the low pressure. That will particularly the horizontal. Yeah, our intention is to discuss mass of the atmosphere. That is one case. Then composition of the atmosphere. What's the Earth's atmosphere is composed of? Earth's atmosphere is a mixture of permanent gases, fine, gases with variable concentration, variable gases, solid and liquid particles. It is another way of classifications. Preferably go with the two case, permanent gases and the gases with variable concentration. What permanent gases? They are saying that if you see the bottom picture with the diagram, the lowermost, the black color is the solid surface, then troposphere, then stratosphere, then moon, you can see that. Permanent means it should be, the composition should remain constant with time. Composition also should remain constant with the space. For example, if I take a sample over Bangalore, Gnanabargi campus, if I take a sample over Malleshwaram or maybe Chenpatna, it should remain constant. Do you agree that the composition of the atmosphere remains constant between Chenpatna, Ramnagara, Kollagala, Mysore, Mandya, over the land, over the agricultural land, over the forest, over the desert, over the ocean, over the river, over the Himalaya, over America, over India, over polar region? Yes, it has to remain constant. Especially, how far? Maybe starting from surface till to the extent of the 100 kilometer, you can go vertically upward. Wherever you take a sample, the contribution remains constant. Preferably, that is why those gases are called the permanent gases. Means their contribution also does not change. You take a sample either morning or afternoon or evening or during winter or during summer or during rainy season. Means to say 98 out of 100%. Okay, if you mark them all of them put together, 78% of nitrogen, 21% of oxygen, 0.9% of argon, and rest of them as the trace elements. What you got it. We'll discuss in next slide. No issue. The contribution wherever you take by volume means 1 meter cube air sample if you take, 1 kilometer cube sample you can take, actually you will get 78% contributes to the nitrogen, or 78% of nitrogen should be there, 21% of oxygen should be there, 0.9% of argon should be there. Means that is the composition. Means this concentration does not vary from place to place. This concentration does not vary from time from last billion years. This is the contribution, it is remaining constant. Means forget about 4.5 billion years ago, where there was no oxygen of that kind. Atmosphere is maintaining from last several centuries, several hundreds of centuries, the same composition. That is why. But still people are worried. Why we are worrying? Because atmosphere is changing a lot. Climate changing a lot. Earth is getting warmer and warmer. Maybe life may not be possible on Earth. There are several protocols Tokyo Protocol, Japan Protocol, IGAC Protocol, IPCC Protocol. That is all of them are for the gases with variable concentration. Gases with variable concentration. In the sense, compounds of carbon, like carbon dioxide, carbon monoxide, maybe compounds of sulfur, sulfur dioxide, sulfur trioxide, sulfuric acid. There may be compounds of you can call sulfur, compounds of hydrogen, compounds of carbon, like H2O, HO2, H2O, H2O5, compounds of rest of them. Their concentration is far be less, still they make success. Third category is the one where the solid and liquid particles can happen. Solid and liquid particles are nothing but some of the particles in the atmosphere always they will try. In the sense, they are not water vapor content actually, means they are the dust particles. They are the dust particles. They are the mixture of the solid and the water liquid, not the gases constants. Means like dust particles. Dust means need not be dust of a sand, dust of any bone of that kind. Their size varies from several nanometer till to the extent of few millimeter, maybe 0.1, 0.2 millimeter of that kind actually. They are called the solid and liquid particles. They are called by a name called aerosols. Aerosols. Aerosols are the suspended particles in the atmosphere. Here, what I told, the permanent gases are the one. Their relative fractions of nitrogen, oxygen, and argon, etc., remain same if air is sampled at either Hassan, Bangalore, Antarctica, North Pole, at the surface, or at different heights up to 100 kilometers. Up to 100 kilometers. Good. I hope you got this slide. Don't worry. When we refer this, normally we have to say the when it was taken, in the sense when this number was taken actually. Means if I refer a book with 100-year book, maybe a tough task. If I refer a book with recent publications, maybe a number may vary to some extent, not for permanent gases. Nitrogen, you can see 78.084% by volume, by 1 meter cube or 110 kilometer cube or 1000 kilometer cube, the same thing, or 1 centimeter cube. 78.084% of the nitrogen, 20.946% of the oxygen, second largest element. Okay, 0.9, third largest element of argon. Okay, if you combine all of them put together, you will get about 78, 20, almost 98. This you add 99.9. 0.999 should be added here. No, 9 is 88, 99.8, almost 99.9. Okay, but thing is that rest of the gases is hardly about 0.04%, 0.03 to 0.04%. Here, this is another number, carbon dioxide. Carbon dioxide changes from time to time. This is 0.037% or 370 particles per million was long number about 2020, not 2020, about 2010 actually. Right now, this number became 0.041, 0.0412 of that kind, 0.012. 0.041 or 0.042 of that kind, means almost 410 to 412 particles per million is the amount of the carbon dioxide existing in the Earth's atmosphere. Rest of them are the trace gases here. All other gases you can call like neon, helium, methane, hydrogen, even ozone put together constitutes the trace gases. The atmospheric composition is in balance. If not in balance, life becomes miserable. Permanent gases, what you expect, see that how they can go. This is the major contribution. Molecular weight of nitrogen is 28. This is 14 times N2. That is why 14 into 2, there are two diatomic molecules. 14 into 2, 28. By volume, it occupies 78.084%. Okay, 0.084%. By volume, 1 meter cube. Oxygen, 32, that is a 16 O. Okay. Then argon, 40. Okay. This is 0.934. This is the mass fraction they can call, but this is by specific gas constant actually. You don't expect always 1006 is the gas constant for real gas, ideal gas. For atmospheric gases, it should be about 296. Nitrogen and oxygen they will put together, it's about almost 300 they can call. Okay, no issue. Leave it, the last two columns. Go ahead with these two. This is fine. Neon contribution is about 1.8 multiplied by 10 to the power of -3. So much small fractions. Variable constant, for example, water vapor. Water vapor is the beautiest vapor constituent here. The concentration varies from 0.01% to almost by 5% by volume. If it is a dry region, you may not get water vapor to a dry region, you may not get. If it is in moist air, you may get more. Means humid air, humidity will be more during the summer. If the temperature is more, you will get more humid. If the temperature is less, you will get, that is cold regions doesn't have water vapor. During December, you may not have the water vapor, much of the water vapor in the environment. There is a misconception in such a way. If the atmosphere is cold, don't expect much water vapor, you expect less. That is why during December or during winter season, people will preferably use moisturizer because skin gets break, skin gets cut, mainly because of the less or lack of moisture in the environment. If there is no moisture or much moisture in the environment, we have to adapt. We have to use the external moisture to maintain the skin cuts. We can call means during summer, like March, April, May, June, July of that kind, in even though including rainfall, what you expect, the amount of water goes up more. That is why moisture content also more during the summer. Carbon dioxide, that's what I told, almost molecular weight is 44%. That contribution also changes to a great extent. Methane, another agent. Ozone, another agent. Sulfur dioxide, another agent. Compounds of nitrogen, compounds of carbon, so much. They are called the variable gases. Their contribution does not remain same in the atmosphere. It varies from time to time. It is an average value. It also changes from place to place. For example, if it is a forest, near the forest you may get more methane. Near some ocean, you may get different composition. Over deserts, you may get a different composition. Okay, they are the variable constituents. Variable constituents. Green color, where whatever you have shown is that carbon dioxide, water vapor content, methane, ozone, they are active. How they are active? These gases are called greenhouse gases. There, if you allow them with the radiation, they absorb the energy. After absorption of the energy, they emit energy back to the environment. Radiatively active. Don't get confusion with the word radioactivity. They are not radioactive elements. They are active in terms of absorption and emission of radiation in the visible radiation, preferably. They are the agents. They are the constituents where they can absorb the energy which is coming from the sun. They are absorbing the energy which is emitted by the earth and thereby in turn increasing the temperature of the earth's atmosphere. Why people are worried because of carbon dioxide? Because carbon dioxide dissociates into carbon monoxide and oxygen, but carbon monoxide is not favorable for the life to exist on earth. One. Another thing is that the lifespan of the carbon is the air. The lifespan of the carbon in the atmosphere is more than 100 years. They are the better absorbers for the radiation. If they absorb the energy, they emit the energy continuously for 100 years. 100 years means they act like a source of energy and thereby increasing the temperature. During 1960, pre-industrial era, the particle carbon dioxide ratio was about hardly about 280. That has enhanced to the 400 by 2020, and still it is increasing. That is an alarming issue for the climate scientists in such a way that they could not able to make anything in a greater way. The temperature goes on, up and up, up and up. This is another ratio. The radiate composition of the atmosphere near the Earth's surface, that is light, nitrogen, oxygen, and other things. What I told, the same thing is there reflected in the table. It was taken by the reference 2007. This gases variable gas contribution may vary to a great extent. Based on this, one can classify the thing to use an ideal gas law to describe the air properties. For example, pressure should be equal to density times real gas constant multiplied by T. Ideal gas law, what it says that actually the pressure must active P is equal to R times T, N RT R rho times RT. N is for number density, rho is for the mass density. Means depending on the mass of the particle, you can say that. Means if there is a relation like this, you can have a profile for the pressure. He can have the pressure profile for the density. He can have a profile for the gas constant, mass weighted. He can have a profile for the temperature. Means profile in the sense, if the temperature changes, P changes. If density changes, P changes. If P changes, any of those three changes means that the profile of a temperature, profile of a density, profile of a pressure gives us a better tool to understand the atmosphere to a greater extent for us. How it varies, that we will see later actually. Means Earth's atmosphere can be studied as the layers of temperature, pressure, density, composition. So to understand all these things, it requires the knowledge of physics. And your role is essential as a physicist. There is no doubt. Now, I'll stop because I will stop at this moment and let it be prepared for the test only up to this extent. What you expect? What you expect? Rest of them we will take it up after the your intervals. I'll stop here. If there are any queries, I am very happy to take the query and attempt your. I'm trying to convince you actually. Any queries? You can unmute yourself, please. Chetana, I hope you are traveling. Yeah, Monisha, you raised your hand. I'll stop sharing the screen. If there are no queries, thank you. Sorry for occupying you on this Sunday. We'll try. I will try take the regular class on my regular schedule. On this coming class. If there are no queries, you can leave.